Okay. So let's get started. Am I sharing my screen or not? I don't think I am. Here we go. So today's topic is the topic for your last lab next week. So sad, it's your last lab already. But the semester is ending. Okay. So pH and titratable acidity. Let's see what you guys know about organic acids. Organic acids that we found in food. Can you give an example for organic acid? In what food systems? I think Medora wants to give us an example.
Citric acid.
Yeah, citric acid and vinegar. What else? Acetic acid? No, citric acid not in vinegar. Acetic acid in vinegar. Citric acid in lemon and orange and citrus fruits. You can disagree with me sometimes. You can tell me, Pam, you're wrong, but don't put me on your Instagram story. What else? Malic acid in apples. Okay, what else?
Lactic acid.
Lactic acid in? Yeah, dairy. Okay, so in milk products. Tartaric acid in grapes, for example. So these are all organic acids, and what do we know about them? Are they weak acids? Do they have good buffering capacity? Can buffer at multiple PI or pHs, sorry. Is the first one right or wrong? Yes, they are weak acids.
Yes.
Yes, they can buffer because they are weak acids. Weak acids can buffer. They can give protons when you're titrating with a base. They can give you the protons easily so that they can steady the pH. That means they can buffer. Do they buffer at multiple pHs? Think about what group gives a proton in an acid. What is the name of that group, functional group in an acid that can give a proton or pick up a proton? Carboxy group, right? COOH. Citric acid, how many carboxyl groups does it have? You remember from your organic chemistry? Maybe? No? It has 3. Acetic acid has 1. Malic acid has 2. So basically, the carboxyl groups are the groups that are going to give you your protons. They have different dissociation factor. So because they have this different dissociation factor, they will dissociate at different pHs. So if you have multiple carboxyl groups, then the acid buffers at multiple pH based on the pKa of each carboxyl group. The pKa of each carboxyl group is different based on its position. So basically, yes. So all of the above is correct. So they're weak acid, they have good buffering capacity, and they buffer at multiple pHs due to the fact that some of them might have more than 1 carboxyl group. Let's see what you think about this. 2 drinks, they have the same pH. They have, saying here, they can have the same titratable acidity, but potentially different sourness intensity. First of all, when we say titratable acidity, basically percent total acid. Okay, so when we want to determine percent titratable acidity, let's say of orange juice, we will be determining the percent of citric acid in that orange. So that's what titratable acidity means. So what do you think about this statement? True or false, and why?
I think it's true. because you have other components like sugar that can depress, like, depress or sour.
If we don't have sugar,
I would say true because you can have a different composition of organic acids. So would then be different.
so 2 drinks, they have the same pH, the same titratable acidity. Could they have different sourness if there is no sugar, no additive, no nothing? No. So we will see actually that sometimes you have 2 different solutions. They have the same concentration of acid, but they have different pH. Because they have different dissociation of the hydrogen. And the hydrogen ion, the free hydrogen ions contribute to the sourness of the beverage, whatever it is. So this is a false statement. Okay, so titratable acidity, basically here we're defining it, it's measurement of the total acid concentration. Whereas the pH, it's a measurement of the free hydrogens. Again, there are 2 different things. That's why you will measure both in that. There are 2 different things. And sometimes same concentration, I'll show you in a minute here, same concentration of acid. Let's say if I have HCl and I have citric acid. I have 0.1 normal in each. 0.1 normal. HCl almost have more than 95% dissociation in water, whereas citric acid doesn't have that. It's weak acid. It doesn't dissociate readily. So the 0.1 normal and HCl will have very much lower pH than 0.1 normal organic acid, and it will be much more sour. So total acidity affects flavor and is an indicator of maturity. Whereas pH is basically, it measures the active acidity and it measures it impacts reactions. What kind of reactions does pH impact? Yeah. Enzymatic, absolutely different enzyme function at different pH. What else? What can grow in your food? Yeah, microbes. So acidic foods, for example, we pasteurize acidic beverages at lower temperature, shorter time, because you can get rid of the pathogens much more easier than you would do for neutral beverages. Neutral beverages, to get rid of the pathogens, you have to increase the heat treatment more. Also, different organisms grow at different pH ranges, so it impacts the growth. Sometimes you want those organisms to grow during fermentation. Sometimes you don't want your microorganisms to grow. So enzyme reactions, microbial growth, and also chemical reactions. So like Maillard reaction, for example. Maillard reaction favors more neutral pH and alkaline pH. Disulfide linkages that also occur under alkaline pH. Oxidation occurs more under alkaline pH. So the pH impacts a lot of different reactions in food. So it's very relevant measure. Here's the example of HCl 0.1 normal versus 0.1 normal acetic acid. So it dissociates, has a very high level of dissociation. It's not a weak acid, it's a strong acid, so it dissociates readily. And it will have a very low pH of 1 at this particular concentration. Whereas acetic acid, weak acid, you only have up to 3% dissociation, so your pH is about 3 times higher than the strong acid. One other term you will hear a lot is conjugate base. So this is kind of the salt that is when the acid is dissociated or the proton is dissociated. This is the conjugate base. That's another term, so just to remember that. So simple to remember that acid is a donor of a proton, base is an acceptor of a proton. So in presence of water, when you have protons, you form what is known as hydronium ion. So you have hydroxyl and hydronium ion, hydroxyl ion and hydronium ion. At neutral pH, the concentration of hydronium ion equals the concentration of hydroxyl ions, and multiplying this concentration gave you a Kw, which is the ion product constant for water. This is important because it helps us with calculating the pH when we know the concentration of hydronium ion, or when you know the concentration, or when you know the pH, you can calculate the concentration of hydronium ion. So this constant is always one, regardless of the pH. So the concentration of this hydronium ion times the concentration of hydroxyl group is always 1 at 25 degrees times 10 to the negative 24. Negative 14, sorry. So this is the range of the pH from 1 to 14. Okay, so regardless of the pH, the product of the concentration of hydronium and hydroxyl is 1 at 25 degrees C. How does this help us? It helps us in calculating concentrations at a pH of 7. So at pH 7, so the pH is negative log the concentration. So it's 10 to the negative 7. That's why it's a log, negative log. So 1 times 10 to the negative 7 is the concentration of OH minus. What would be the concentration of hydronium ion? Is basically, you can calculate that 1 times 1 and 10 to the negative 7 times 10 to the negative 7, you always get that 1. Okay, so regardless of the pH, the product is 1. So how do we apply this? So this is an example of how do we apply this. Pull out a piece of paper for +2, and let's do some practice calculations. So here we're calculating the pH. I'm giving you the concentration in a 7-up, the concentration of hydronium ion. So you can calculate the concentration of hydroxyl ion, and then using the equation of pH negative log the concentration of hydronium ion, you can get the pH. So just a quick practice. When you have an answer, let me know. So what's the concentration of hydroxyl ion?
2.9 10 to the negative 11.
I got 2.82 times negative 10 to the negative 11. So maybe just a slight calculation difference. Anybody with the pH?
3.4.
Yeah. All right. Yes. So it's just applying the equations basically. So again, practicing how to use your calculator with the log function. All right, so let's do this one. Beer has a pH of 4.3. Calculate the hydronium ion concentration. Basically, here you're doing the anti-log application in your calculator. Do you have a value, a concentration?
-5.01 the negative 10.
Yes. There we go. I do the math a little different, but it's just a matter of using your calculator to get to that value. All right, make sure you have that down. You don't have to worry about the way I calculate things. I'm old school, but okay. So you're going to be using pH meter in the lab, and you'll be calibrating the pH meter. So just a quick high-level introduction of a pH meter and how it functions. So in the pH meter, it relates the ion activity, so hydrogen ion activity. Next week, you're going to learn about mineral analysis, and one of the way to determine mineral composition sometimes is using electrodes specific to the mineral, like sodium electrode. But here in the pH meter, your electrode is sensitive to the hydrogen ion. So, and there is a relationship between the activity and the concentration. So this is a constant coefficient that is constant. Here's the activity, here's the concentration. We don't care about that because the pH meter is going to do the conversion for you and read out the pH of your sample based on the hydrogen ion activity that is going to cause a change in the electrical potential. So when you put your sample in, and then there's your electrode, in there, it's going to measure voltage at a very, very small current. And that difference in voltage will be calculated and give you a pH reading. So you don't have to really know more about that, but we always have a reference electrode and an indicator electrode. So there's a reference that keeps the reading constant based on the reference. And then when you put your sample in, you compare the change in current based on the reference electrode, and that change in current or change in electric potential will give you that pH reading. All right, so pH meter has electrodes. The new ones, you have your reference and indicator electrode in one compartment. Like you will have one plastic container inside of it is having both your indicator as well as your reference electrode. It's the old pH meters, you might have them separate, but most of them are in combination electrodes. So one thing you want to know and you learn in the lab is that you have to calibrate. And we always calibrate using a pH that has 3 units apart. So we use pH 4, pH 7, and pH 10. These are very common 3 points that we use, but you're going to do 2-point calibration with the lab. So you will either use 4 and 7 or 7 and 10, depending on what image. Maintenance is very important. Sometimes you are measuring pH in a solution that say has high protein. The protein might absorb to your glass and plastic and affect your reading. Might take a long time to read the pH. Because sometimes you want to put it in, you put the stair bar in there, usually if you have a dispersion, and you want to wait for that pH to kind of stabilize. If you have contamination on your probe, then it takes a long time for it to stabilize, and it gives you erroneous reading. So you really need to clean your electrode. For, say, if you're using it for high protein solution, usually you clean it with enzymes, pepsin enzyme or whatever, to break down the buildup. Sometimes you use acid to clear any buildup. And if you have high fat, sometimes use alcohol to kind of solubilize the fat layer. So this would be a question in your questions for the lab report. So it's good to know how you maintain your pH meters. Okay, so titratable acidity. Here we're measuring the concentration of intrinsic acid in food. So sometimes in a food you have multiple different acids, but the major acid would be the one that you would account for to determine percent titratable acid. We have citric, malic, lactic, tartaric. Inorganic acids, sometimes they're added to beverages. Phosphoric acid usually is added to beverages. Let's say high protein beverages, they add phosphoric acid to bring the pH down. Sometimes they add carbonic acid. So carbonic acid is not usually added when, let's say, if you take the Pepsi, Coca-Cola, or soft drinks, whatever, and then they would put CO2 in it to become fizzy. The CO2 in aqueous form carbonic acid, brings the pH down. That's why these beverages are usually acidic, because of the presence of carbonic acid. It's simply carbon dioxide in water forms carbonic acid. So to determine titratable acidity, we either use the pH meter and monitor the change in pH until neutralization happens. So you titrate with base. So it's very, very easy assay. It's based on titration. But you would determine the endpoint using an indicator. So you put phenolphthalein indicator, and then you titrate to a pink color. So when you titrate with NaOH, the color changes to pink, and that's how you would determine the endpoint and calculate percent titratable acidity. You can also, instead, which you will be doing in the lab, is you can titrate, but instead of having an indicator, you just, every 1 ml of titration, you measure the pH. And when the pH reaches neutralization, then that's when you stop the titration. So you'll be doing both ways in the lab. So back to the principle of buffering, we talked about buffers and reagents earlier in the class. So just again, buffer is when we resist change in pH, when you have the weak acid and you have the salt or conjugate base. So either we say salt or conjugate base present at the same time, and weak acid have very low dissociation factor. And again, your favorite equation of all time, Anderson-Hasselbalch equation, is where we can use the concentrations we have to to get to a certain pH, or sometimes if you have a certain pH, you can calculate how much of the acid is dissociated versus not. And maximum buffering capacity is when you have equal concentration of the non-dissociated acid and the dissociated salt. When they are equal, then log of 1 is 0, pH equal to Ka. That's maximum buffering capacity. And this is all something you already know and learned earlier on, but we're bringing it back because we need the calculation of titratable acidity. So because it's the titration process, we look at equivalence at the end point when we get to neutralization. So what happens is when you're titrating, you will be titrating and then the acid is going to gradually give you its proton. Very slowly. The pH will resist change, and you keep titrating and titrating until all of your protonated acid is dissociated. When all of your protonated acid is dissociated, this becomes close to 0, you see a spike in the pH, a very quick spike. Once your pH spikes up, that's the end of your titration. And you'll be doing that in lab. You will be watching how the pH is steady, 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 until all of a sudden it goes way up. That means you no longer have protonated acid. And that's when you end your titration. You will be plotting titration curves. And here's where it's very unique for organic acid. If we look at a titration curve for HCl, for example, top one is for HCl. I don't know why I didn't label that. But this one at the top left, that is HCl. So here we see gradual increase in pH until the acid is neutralized. We see a spike in pH, and the midpoint here, if we extrapolate at this midpoint, then you get the milliliter of NaOH needed to reach neutralization, and you use that in the equation. However, if we look at organic acids, there are buffers, and they buffer the most when the pKa equal the pH. So if we look at this one up here is acetic acid. So you have one carboxyl group. So you have one proton here that has a dissociation factor, only one. The pKa of acetic acid for that particular group is 4.75. So what we see here, this is the pH, this is the milliliter of NaOH. We start seeing the pH increases, and then it kind of like slows down. It resists change when the pH equals the pKa. So we see some like flattening here a little bit. And then when we pass it, it continues to increase, it spikes, neutralization, equivalence point, you get the milliliters needed to reach the equivalence. If we look at citric acid, and that we're going to plot malic acid, and we're going to titrate apple juice. So here we have 1, 2, 3 carboxyl groups. So you have 1, 2, 3 hydrogen with different dissociation factors. So each of this group having a different dissociation factor, we'll see the titration curve here plateauing at 3 different pKa's. So if an exam, I tell you draw the titration curve of citric acid, you want to show, you don't have to remember unless I give it to you in the exam, the pKa. You would just draw some plateau around those 3 different points. And then the pH increases and then spikes when the neutralization happens, when all of your acids is, or all of your acid is dissociated. Okay. All right. Let's do some practice here. You have pH 4.7. And in lactic acid, you want to determine percent of lactic acid at this particular pH. Or sorry, you want to determine how much of the lactic acid is dissociated. So you want to determine the concentration of conjugate base at pH 4.7. And this is the pKa of lactic acid. So here you want to apply the pH equals pKa plus log A minus. A minus in this case here is lactic acid that is deprotonated over concentration of the acid with the proton. So I'm asking you to calculate this if you have the pKa and you have the pH. So you just apply the equation. You want to remember that this concentration of A minus plus concentration equal 1, the whole, okay, 1 or 100 or whatever is the unit. So that's in this case, you want the percentage, so this could be 100% instead of 1. All right, anybody with an answer? Go ahead, Lisa.
Right, but I got 0.17.
0.17.
But that's without.
I think have that, Priyanshi. 87%. So with what you want to remember is just you want to apply, you want to substitute here. We're solving for A minus concentration. We have, you can put a 1 here or 100 minus the A1, A minus concentration. You just substitute here. And you just get the value after you get the log. So you get that value and you just do your algebra here solving for X, you get 0.87 if you use 1, or you get 87%. And we're looking for a percentage that just a matter of, again, using your calculator correctly. Okay. All right, so equivalence point. We measure it using a pH here. The problem with that is it's sometimes you have a slow response, you keep titrating, you can overshoot until to wait for stabilize. So you really want to do a little bit, a few drops at a time and wait for the pH meter to stabilize. But we can use indicator if your solution is clear. So you're going to be measuring percent of citric acid in think the 7-Up or some other beverage, maybe 7-Up, I don't remember now. But there's apple juice and there's 7-Up in the lab. For 7-Up, it's very easy. You just clear solution. You can put phenolphthalein indicator and the color changes from clear to pink or red in the range of pH 8 to 9.6. So when we're titrating, when we reach the pH 8, the color changes. And we usually get to the pH of 8.2 and food acids, organic acids don't buffer at this pH. So we are in the safe zone. Why is the endpoint pH 8.2 not 7? Can anybody guess? Kind of trick questions like why you talk about neutralization and then it's not 7, it's 8. Especially when you have organic acids. It's not the case when you just have like HCl itself. Because the conjugate base, right? So the salts have higher pH. So the conjugate base drives the pH a little higher at neutralization or complete take up of the acid. All right, so in the lab, you will either titrate until you see pink color using phenolphthalein, or you're going to titrate until we get pH 8.2. We don't have a problem there when you're using natural organic acid. You won't see buffering at this pH, and that would be the endpoint. Now, the problem is when you have inorganic acids like phosphoric acid or carbonic acid. So these acids buffer at this pH. So we can easily overshoot if we're using phenolphthalein. We're going to buffer, we turn pink, and the pink fades over time. So instead of for beverages that have these inorganic acid, what we do is just pH. I mean the pH. Once we get to pH 8.2, we stop the titration. Then the minute we get to pH 8. Otherwise, if you're titrating, you're going to stay at pH 8.2, but then you will be overshooting the titration. So as soon as we get to pH 8.2, we stop the titration. And we use pH meter also when you have maybe dark color. So if you're looking to native juice, for example, it's dark red, or grape juice, it might be already purple, and then it won't be able to do an indicator. So we use a pH in this case. So in the lab, you're going to standardize an NOH solution. We need to get the exact concentration of NOH because you need to use it in the equation. And usually your percent organic acid is very, very small concentration. It's oftentimes around less than 1 or around 1%. So if you have not standard concentration of NOH, you will over or underestimate your acidic titrated acid. So you need to use the exact concentration that you prepare. So you weigh out NOH, you put them in solution, you bring up to the volume. You're not going to have exactly 0.1 normal. It might be 0.12, 0.108. You really need to have that number. So we prepare the reagent and we make sure that we can standardize it, and you're going to standardize it with a standard acid, which is potassium acid phthalate, is what you're going to use in the lab to standardize your NOH. Now, another thing that we're going to do in the lab is use CO2-free water. Because if you have CO2 in your water, what acid is going to form? If you remember? Carbonic acid. And carbonic acid is going to cause an overestimation of your titratable acidity. So you don't want that. So you're gonna use special water in the lab next week that has been boiled to boil off carbon dioxide. And then you're gonna see an asteroid trap at the end of the flask. So you will have a volumetric flask that has water that has been bound, the boil, and then there will be a tube connected to an asteroid trap, which is silicon coated with NaOH. The NaOH is going to trap any excess CO2 you have in the headspace of that reagent. Because you don't want any CO2 there. Because if you have CO2, it's going to change even the concentration of your NaOH. Why? Because if you have NaOH and you prepare it with water that has CO2 in it, you're going to form sodium carbonate. This is going to precipitate is going to change the concentration of your NaOH. Okay, so a couple of things happening here. You don't want carbonic acid in your sample, but at the same time, you do not want your reagent to have carbon or sodium carbonate, because that will precipitate out and change the concentration of your NaOH solution. So that's why it's very important when we're doing titratable acidity, we prepare NaOH with CO2-free water, and then we standardize it to make sure we have the correct concentration. And then calculation, we have derived this equation like many times before, but one thing is new here. The one thing is new is instead of molecular weight, we're going to look at equivalent weight. Why? Because every acid has a different number of equivalents. This is very important, you guys. If you have acetic acid has one carboxyl group, so the molecular weight will be the same as the equivalent weight. Molecular weight equals, well, equivalent weight equals molecular weight divided by number of equivalents. If you have more than one carboxyl group, you have more than one hydrogen in the reaction. Okay, so if you have two carboxyl groups, you would have to divide by 2 to put it in this equation, because you have two hydrogens in the reaction. If you have three carboxyl groups, you have three hydrogens in the reaction, so you want to account for that. So you would divide the molecular weight by 3. Everything else is the same as we derived earlier. So normality and volume of your NaOH, that's why it's important to get the exact normality, the volume of titration, divided by the rate of the sample, correcting milliliters to liters. And then because it's a percentage, we multiply by 100. So one thing you want to remember here is the equivalent weight, because we can be working with more than one hydrogen in the equation. When you are titrating, that we would be having multiple hydrogens taking part in the neutralization step. So with that in mind, here, I give you the molecular weight, and then I tell you, or I draw, so you see 3 carboxyl groups. All right, so apply the equation. Sometimes in the test, either I draw this, or I give you the 3 pKa or 2 pKa, then you would know that, oh, I need to account for 2 hydrogens, I need to account for 3 hydrogens, then you know what you would divide the molecular weight by. Kevin, you have a value? Anybody? We're just applying the equation from the previous slide, knowing that you need to divide by 3 here, the molecular weight, because you have 3 carboxyl groups. What do you get, Kevin? What do you have?
0.5%.
0.6%.
Okay.
Yeah. So I told you that the standardized concentration is 0.08 moles per liter. You use 75 or 17.5 milliliter to reach to the endpoint. The equivalent weight is divided by 3, so it is 64 grams per mole. And then here, instead of doing, because we're doing percent, it's okay that we have volume, not grams in this case. It's milliliter per 100 milliliter of sample. Then we divide by the volume of your sample and divide by 1,000 to correct for milliliters per liters. So it's basically, sorry, here it should be milliliters per 100 milliliter, the percentage.
Do you want that unit there, or are you okay with percent?
Percent is fine. I
Okay.
just, here it should be like that. Because it's milliliter and south. Percent is just fine.
Well, it still should be grams though, because you have that gram there, the grams per mole is still remaining. You have moles per liter cancel. Right.
I have to cancel my units. So the moles cancel. The milliliters cancel.
The question asks for weight per volume too, so it's okay with grams per milliliters.
Oh, okay. I confused myself.
Okay.
Then no. Yeah, it is. Oops. I had it correct the first time. Okay. Thank you, Kevin. All right. Any other questions? All right. So here's the table, FYI, is that if ever in the final I give you calculations, when you calculate, you want to make sure that your values make sense. So they're all almost under 1 with very few sample acidity that is over 1%. So usually your titratable acidity is really low. So this is FYI to remember, titratable acidity is usually low. So so when we calculate titratable acidity, just a second, 30 seconds, I'm done. Titratable acidity is you calculate based on the predominant acid. So use the molecular weight of the predominant acid. We use the Brix to acid ratio to predict the acid flavor here because of the presence of sugar that you have. And the last thing here, we can measure volatile acidity. So this is a measure that is especially done in wine. So if you have acetic acid, the vinegar flavor, you don't want that in your wine sample. So as a quality measure, you determine the amount of acetic acid you have. You measure titratable acidity of the wine. You boil to evaporate acetic acid, and then you measure titratable acidity again. Then you can determine how much acetic acid was there, vinegar flavor. All right, so next week you're going to be doing your last lab on pH on titratable acidity. You're going to do standardization, doing some calculations in lab, and that would be the end of lab. Next week, Monday and Wednesday, you have a guest lecturer. You're going to cover, this is Dr. Dan Gallagher. He's an expert in vitamins and minerals, so he's going to cover vitamins and minerals analysis with you guys. He's very entertaining. I hope you enjoy him, and I'll see you next Friday.
Ma'am, I have a question. So, with this lab report, it was due on the 12th. Are we gonna see lab report on the 12th?
Tomorrow, Pat will talk to you next week about lab report due date. We will be very considerate of your time. But I won't say no more. All right. Oh, last thing, don't forget, evaluation of teaching. Please, I rely on your positive and negative feedback, constructive feedback. So please fill out those for the extra +2. Yes.
Do we need to fill out the rest of our lab notebook for lab 13 or? do we
Yes,
have
you-
everything that check for that after lab 13 stuff?
After lab 13, you're not getting your checks, but next week you'll get the lab.
Okay, so once we like, basically we don't need to do those results calculations in our lab note.
Unless you like it.
Okay.
Okay.
Well, we can,
Oh, like